So today we're going to talk about using frequency distribution to understand data. Bottom of page 45. Bottom of page 45. Flip the page. It says something about a normal distribution here. Okay. Data that have an approximately normal distribution are characterized by a frequency distribution with the following features. The normal distribution is the gold standard of statistics. All statisticians wish and hope that they can classify or call whatever it is, the population distribution, a normal distribution. The reason being is because there is so much research done about the normal distribution. This is commonly referred to as the, I'm sure you've heard this term before, the bell curve. Okay, this is the bell curve. When you guys commonly ask your teacher to curve the test, okay, when you ask them to curve the test, you're asking them to put it into a bell curve, okay? Instead of having, you know, something that, a dot plot that looks like this on your test, right? If you can somehow make this into looking like this, some of these people are going to go up, hopefully, right? And he's going to go down a little or whatever, and it's going to look like this, and there's less of a difference, right? I mean, isn't that what you guys ask when you want us to curve the test? Okay. All right. So, bell curve. How would you describe this? Besides the fact that it looks like a bell. How? What?
Starts low, goes high, and then...
Yeah, it starts low, and then goes high, and goes, which means there's a lot of stuff in the middle, right? So commonly you guys know, you guys have heard of this before, right? Mean, median, and mode, right? Okay. Median is what? Well, let's do the mean first. What's the mean?
Average.
It's the average, right? You just add them all up together and you divide it by how many there are, right? Where do you expect the mean to be here on this curve? Right down the middle. Right? That's where you expect the mean to be. Right? Which also gives us a very interesting characteristic of this curve. This curve is actually, it is symmetric across the middle. A true normal distribution is symmetric across the middle. Okay? What is the mode?
Frequent number.
The one that comes up the most, right? Which one would that be? The middle, right? You can see it has the most dots, right? It's the highest peak, right? Which means that the mode and the mean are the same. What's the median? How do I find the median? Huh? It's the one that's in the middle, right? So you stack them from low to high, right? And you go all the way and you find out what's in the middle, right? That's the median, okay? Where's the median here? Same place. So in a normal distribution, the mean, median, and the mode are all the same. Well, isn't that nice? Right? They're all the same. Okay? They are reflective across each other, and therefore I can do many different studies about this. Okay? And we'll get into that we'll get into that second half. I think it's second semester. But we will be talking about normal distributions quite a bit. Okay? So just realize that. So, normal distribution, number one, the frequencies start low, then increase into one or two high frequencies, and then decrease to a low frequency. Number two, distribution is approximately symmetric. Frequencies preceding the maximum frequency should be roughly a mirror image of those that follow the maximum frequency. Okay? All right. One of the things that statisticians like to say is that they're not going to tell you yes, and it's exactly a normal distribution. But they're going to say it's roughly asymmetric, it's roughly a normal distribution, or we can consider it to be a normal distribution. Okay, all right. So just whenever you hear those words, understand what's going on there. Okay. Go to page, jump in the middle of page 46. There's a table 2.6. Frequency distribution showing a normal distribution. You can see that the 2, 8, 30, 8, 2. That is definitely symmetric, right? 2, 8, 30, 8, 2. Okay, so it's definitely symmetric, and definitely it is a single peak there in the middle. Okay. Analysis of last digits. Frequency of last digits sometimes reveal how the data were collected or measured. Okay, what does that mean? Let's go ahead and read example 3 there. Okay, let's have Kayla read that for us.
Upon examination of measured pulse rates from 2,219 adults included in the National Health and Examination Survey, the last digits of the recorded pulse rates are identified, and the frequency distribution for those last digits is shown as shown in table 2-7. Here is an important observation of those last digits. All the last digits are even numbers. If the pulse rates were accounted for 1 full minute, there would surely be a large number of them ending with an odd digit. So what happened? One reasonable explanation is that even though the pulse rates are the number of heartbeats in 1 minute, they were likely counted for 30 seconds and the number of beats was doubled. The original pulse rates are not all multiples of 4, so we can rule out the procedure of counting for 15 seconds and then multiplying by 4. Analysis of these last digits reveal to us the method used to obtain these data.
Keep on going. We're almost there.
In many surveys, we could determine that surveyed subjects were asked to report some values, such as their weights, their heights or weights, because disproportionately many values end in 0 or 5. This is a strong clue that the respondent is rounding instead of being physically measured. Fascinating stuff.
Okay, great. So if you look at that table, look at the table, right? You have 0. There's nothing in 1, 3, 5, 7, and 9. Right? Okay. So they inferred from that okay, well they must have just did 30 seconds and multiplied by 2, right? So what would be a good way to get around that? So you don't have data that looks like this. I mean, data that looks like this really is kind of, I don't want to say useless, but you have the zeros there, right? So wouldn't you rather just do the 0 through 9 and say instead of 1 minute we did 30 seconds? All right? Okay? See what I'm saying there? Okay. Okay, that's that. We're there. So on the top of page 47 it says the presence of gaps such as this can suggest that the data are from 2 or more different populations. Okay, this is different. This is a different one. Okay, so let's go to example number 4. Example number 4. The gist of this is that if you look at the table 2.8, there's a frequency there. They had measured the weight of a penny. And what can you say about the data? There is 18 and 19, and then there's 2, 25, and 8. They're clustered, right? They're 2 separate clusters. Okay? And so what happened here is the pennies made before 1983 are different composition. They're 95% copper, 5% zinc. But after 1983, there were 2.5 copper and 97.5 zinc. Okay? That's why there's a huge disparity. There's a difference there. Okay? Why, does anybody want to guess why we are not using copper anymore? Because copper was 95%, now it's only 2.5%.
So, wasn't the amount of copper they used worth 2 cents in 1 penny?
That was true. Okay, so the copper was going up. The cost of copper was going up, the cost of pennies were too much. So they said, well, this isn't going to work. So they changed the copper, all right, to now it is made more zinc than it's copper, and zinc is much cheaper. Okay. Okay, and then in example number 5, combining 2 or more relative frequency distributions in one table makes comparisons of data much easier. So if you look at table 2.9, they compare, so you have 2 different, so they combined the Dunkin' and the McDonald's kind of together so they can actually see the difference, right? So if you're Dunkin', you're looking at this data and saying what? What are you saying? What are you thinking? We're faster. We're better than McDonald's, right? We can sell a lot more in a shorter period of time, right? If you're McDonald's, what are you saying?
We get faster.
Okay, what? Our food's better. Okay. You can also say what? We're not selling donuts, right? We have to like assemble stuff, actually make the stuff. Whereas in donuts, you're just basically taking it off the rack, right? And putting it in and just kind of moving on, right? Okay.
And those places are actually really slow.
What? Okay, so, all right, we're done. We're done for the day.